Good day everyone and welcome to the class. So this is our first video lecture. In this lecture, I will be discussing or we will be reviewing some of the most important or often overlooked aspects of mathematics and science that will be very helpful in your study of chemical engineering calculations. So this is just a review, okay? Now, I have uploaded the PowerPoint presentation to our Blackboard, but for this video lecture, I would like you to simply focus on this video because the presentation is also in this video. So we have several different modes here. We have a discussion scene wherein I can write something. This would be very helpful if we will be solving problems, so you can follow along with my solution. And we also have our window for the presentation itself. Okay, and with that, let's get started. So this is lesson one, a review of the fundamentals. So this is very important, no? Because we don't want to progress in this course without addressing some of the most important things that you should be reviewing or you should be preparing for this course. So let's start with an outline of this lecture. So in this lecture, we will be talking about measurements, fundamental and derived quantities, units, some use of numbers. So we might be skipping some of these parts because this lecture is made for high school students just to refresh your memory on how to properly use numbers. And then the last would be the conversion of units and dimensional analysis. Okay, let's begin. Measurements. So when we are talking of measurements, we are largely talking of two groups of measurements. We have the fundamental quantities and the derived quantities. So fundamental quantities are exactly seven. No? These are the quantities that cannot be derived from any other source. So they must be fundamentally defined. So these fundamental quantities are length, mass, time, electric current, temperature, luminous intensity, and the amount of substance. So in contrast to those fundamental quantities, we have the derived quantities, wherein these are just some examples. No? We have volume, density, speed, force, pressure, work, and many more. So we are not limited to seven derived quantities. So let me give you an example of a derived quantity. So one example that was mentioned was density. So we represent density with the Greek letter rho. And in terms of a formula, we define density as the mass of a substance divided by its occupied volume. Now, if you would go back to to our presentation, the derived quantity is the density. And since we know that this is a derived quantity, this must be made up of several fundamental quantities. So let's take a look at what are the following fundamental quantities in the definition of density. You see here that volume is not a fundamental quantity, no? So volume is another derived quantity, and we must also define volume in terms of its fundamental quantities. So mass is a fundamental quantity, no? So how do we get the fundamental quantity of volumes? So it depends. Let's say, for example, that your substance is a cube. So if it's a cube, the volume is simply side squared, wherein the side is a unit of length, where the side is now your fundamental quantity. So you see here that our two fundamental quantities that are used to derive density are the mass and the length. Sorry, volume is side cube. Okay, so we have the mass and the length as fundamental quantities, which are vital in determining the value of a derived quantity, which is density. So in our future discussions, you would be encountering a mix of fundamental quantities and derived quantities. So it's very important that you know their differences. So another way that we can tell if something is fundamental or derived is how is it measured, or is measuring it is actually measuring it the only way of determining its value. Let's say, for example, temperature. So the easiest way to tell the temperature of a room is to look at a thermometer, because a thermometer directly measures the temperature of the room. So therefore, temperature is a fundamental quantity. Of course, you can solve temperature using other methods, but those are all derived methods, no? So and that uh, those methods do not count. So the same goes well with mass. So how do we measure mass? You use a balance to determine how much does something weigh. And time, how do we measure time? We use a stopwatch. No? So the fundamental quantities are all measurable, while some of the derived quantities may also be measurable, but largely they are derived from our fundamental quantities. Next. So in terms of units, for every fundamental quantity, we have the base unit in the International System of Units, or the SI system. In the Philippines and in majority of other countries, we are all using SI units. We are using SI units because they are very easy to handle, especially with the use of prefixes, which we will be discussing later. So for the seven fundamental quantities, we have the seven base SI units. So for length, it's meter. For mass, it's kilogram. Time, seconds. Electric current is amperes. Temperature is Kelvin. Luminous intensity is candela. And the amount of substance is mole. Now, these base units could either be enlarged or become smaller by the use of what we call prefixes. Okay, so SI prefixes are very useful in expressing very large numbers or sometimes very small numbers. Because when we are expressing numbers, oftentimes you don't want to see a lot of zeros for small numbers. Let's say, for example, 0.00000000001. No? So we want to express those in terms of prefixes. So here are some of the most common SI prefixes. We have giga, which means 10 to the ninth power, or 1 billion. We have the mega, or 1 million. The abbreviation for mega is capital M. For giga, it's capital G. So you might be noticing something here. If it's a big multiplier for a prefix, we normally use capital letters. And if it's a small multiplier, we use small letters. Okay, kilo, we use the small letter K. We don't use the big letter K to not confuse it with Kelvin. No? So that's 10 raised to 3, or 1,000. Centi means 100, so that's 10 raised to negative 2, or sorry, it means 1 of a 1/100th, or 1 of a 100, 1 of 100. The abbreviation is C. We also have milli, or 1 over 1,000. Micro, 1 over 1 million, and nano, which is 1 over 1 billion, or 10 raised to negative 9. So you must be familiar with these prefixes because we will be using a lot of these prefixes during our calculations. Okay, so these are just some basic examples. So express the following quantities into their appropriate SI units with prefixes. So we will be doing just two of this, one very large number and one very small number. No, in order for us to take a look at the on how do we use, or how do we properly use prefixes. So let's try number one because that's a big number. So let me just copy it first, 236,100 meters. Okay. So how do we appropriately apply prefixes to this number? Now, you might argue that this is not that big of a number and we can just report it as is. But this is still a big number, and you can shorten this using prefixes. Now, one of your options is to use the prefix kilo. Remember, kilo means 1,000. So if you divide 236,100 with 1,000, or if you move it 3 decimal places, you get 236.1 kilometers, or kilometers. If you go one step further, you can move the decimal place into 6 places to make it mega. So that's 1, 2, 3, 4, 5, 6 to make that 0.2361 mega meters. Now, obviously, all of these are correct. So all of these three expressions of the same number are correct, but one is more appropriate than the other. So first, we normally do not use mega meters because it is often confused with other units, such as uh, you can The capital M could stand for molar, although in this case, molar cannot come before its prefix, so we cannot confuse it for that. But we just normally do not use megameters as a unit. So in this case, the kilometer or the kilometer is a much more appropriate unit, or is a much more appropriate presentation of the data. Okay, so let's have another example. Let's use a very small number. So let's use number 4. That's 0.1234557 amperes. Okay. So we have 0 followed by 0 points, then followed by 5 zeros, and then 5 7 amperes. So amperes is a base SI unit. It's a fundamental quantity. So this is a very small number. So we need to use the smaller prefixes in order for us to remove a lot of the zeros. The only purpose of us using smaller prefixes is we do not want to see this many zeros. So it takes longer to write, and you are more prone to errors if you are writing many zeros. So let's lay down our options. Our first option is to move this 3 decimal places to the right. 1 2 3, you get 0.0057. That is milliamperes, because we moved it by 3 decimal places. That's a factor of 1,000. Okay, but this still has 2 zeros, so we can still move this. If we move it by 1 2 3 4 5 6 by 6 places, you get 5.7. Sorry, you get 5.7 micro amperes. So in this case, the more appropriate way of representing this is 5.7 microamperes. We have eliminated the use of zeros, thereby eliminating some possible sources of error, and we have shortened the notation to just 5.7 microamperes. Okay, so that is how we use SI prefixes in order to shorten our presentation of numbers. So this would become very handy in our future lessons. Okay, moving on. The English system of units was once the internationally accepted set of units worldwide. But then after some time, we realized that the English system of unit is very difficult to use, or it's very confusing. So let me give you an example. So in the English system, let's consider units of length. So in the English system, we have inches, feet, yard, and miles. While in the SI system, in order of increasing magnitudes, we have micrometers, millimeters, meters, and kilometers. So in order for us to see why the English system of units is such a hassle to use is through an illustration. So let me give you an illustration. Under the SI system, we are moving in multiples of 1,000. So it's very easy for us to convert. So for us to convert, let's say for example, from micrometers to millimeters, we can use the conversion factor. 1 millimeter is 1,000 micrometers. If we move further, 1 meter is equal to 1,000 millimeters. And if we move further, 1 kilometer is equal to 1,000 meters. So it's very easy to understand. It's very easy to remember. We are moving by multiples of 1,000. But the same is not true for the English system. So let's first see the conversion from inches to feet. 1 foot is 12 inches. So that might be easy to remember because you are already familiar. But then if we go from foot to yard, 1 yard is equal to 3 feet. So there is already a discrepancy, no, between yards to feet and then feet to inches. And then further, if you convert yards to miles, 1 mile is 1,760 yards. So you see here, no, there is a very big discrepancy between the jump and the conversion values when you are going beyond units. So, and this is just in length. If we go to the English system, units for mass and for volume, it gets very, very confusing. You have the pounds, the stones, the ounce, the gallons, and etc. Okay, so in the majority of our problem solving cases, we will be using the SI system, but sometimes we will be using the English system. So later on, we will be dealing with conversions between English and SI system. Okay, moving on. So we will just power through, or we will just quickly browse this next part, the use of numbers. What I really want to highlight in this section in the use of numbers is sometimes it gets very annoying on how students represent numbers. This includes rounding off, scientific notation, the use of significant digits, or the use of significant numbers or significant figures. Because the one thing that irritates me the most is when you are giving an answer and you are writing all of the decimal places. No? I would be illustrating that later. Let's first discuss rounding and truncating. And there is a difference between rounding and truncating. To round off means to stop at a certain digit or decimal place and increase or decrease the digit of the place depending on the digit adjacent to it. Okay, so you already know how to round off or round up. Now, to truncate means to stop at a certain digit or decimal place and discard the rest of the digits regardless of the adjacent digits. So to truncate is to simply disregard all of the other digits without either going up or remaining the same. So that is not the same as rounding off. Okay, so I just wanted to point that out. Next, scientific notation. So I hope no that you already know how to write in terms of scientific notation, because if you don't know how to write, then you seriously need to review this. So we use scientific notation to make very large or very small numbers presentable. So examples are this one. So this number one, 3, and 4 are very large numbers. The way on how we make this presentable is we move the decimal place to the left until we only have one remaining digit on the left of the decimal place. No? For very small numbers, we move the decimal place to the right, and the purpose of that is for us to remove the zeros. No? This is the same concept as we use in the SI prefixes. Okay. Now, this is the most important part, significant figures. So significant figures are the digits that we are sure to be correct. We don't need too many digits in our measurements, and for your case, you don't need too many digits in your final answers. So let me give you an example. Does any of the following make sense? First, if I instructed you to measure, or if I instructed you to buy rice, so let's say, could you please buy 1.361224 kilograms of rice? Would you be able to do that? You would not be able to do that exactly. First, because there is no commercial measuring scale, or there's no commercial weighing scale that could accurately measure exactly 1.361224 kilograms of rice. Even with the most advanced laboratory analytical balance, you will not be able to measure this amount. Next, if I ask you to please cut 12.018696 inches of string, that also does not make any sense because you would not be able to measure that accurately. And lastly, I would ask you to measure or run in 15.2397518175028 seconds. That would be impossible for you to do exactly. The point here is we normally do not need that many significant figures or that many decimal places. So the question is, how do you determine if two decimal places is enough, or how do you determine if this amount of significant figures is already enough? to convey your final answer. So we have some rules. I hope that you already know these rules. No? The rules for significant figures are as follows. First, all non-zero digits are significant. For example, the first one, 35347, that's 5 digits, 5 non-zero digits. Therefore, that number contains 5 significant figures. The second example, 851, there's 3 non-zero digits, so there's 3 significant figures. Next, zeros that are used to define the placement of the decimal point are not significant, or they are not counted. For example, for the first one, 0.000012, the zeros preceding 1, 2, those are not significant. The first example, there's only 2 significant figures. Next, for the next example, we have 4 significant figures. The only ones that are significant are 4, 1, 5, and 3. So that's 4 significant figures. Last, zeros are significant when they are in between non-zero digits. Okay. For the first example, 1.002, the 2 zeros are in between 2 significant figures, so they are counted. So in 1002, you have 4 significant figures. And in this example, you have 1, 2, 3, 4, 5, 6. You have 6 significant figures. Okay? If the zeros are sandwiched in between significant figures, then they are also significant. Next, zeros placed after non-zero digits to the right of the decimal point are significant. So 23.500, these two zeros are both significant. So we have 5 significant figures. And then for the number 1.000, you have 4 significant figures. Okay. Next, zeros placed after a non-zero digit to the left of the decimal point may or may not be significant. It should be converted to a scientific notation to make sure if it's significant or not. So the number 250,000 could either have 2 significant figures if you're only counting 2 and 5. If this first zero is significant, then we can have 3 significant figures. We can also have 4, 5, or 6 significant figures. So the answer varies a lot. To further illustrate that, let's see the number 250,000. If I write this number as 2.5 times 10 raised to 1, 2, 3, 4, 5. In this notation, 2.5 times 10 raised to 5, this has 2 significant figures because we are only counting the 2 and the 5. But if I write it as 2.50 times 10 raised to 5, then we now have 3 significant figures. Because remember, all of the zeros that come after the decimal point to the right are all significant and they are all counted. So we can also have this in as many significant figures as we want. So this is 4 significant figures. Okay, so that is how we discern on how many significant figures are there. And then, okay, sorry. Lastly, all digits to the left of the exponential term in a scientific notation are significant. That is what we have done in the previous example as well. Okay, now here comes the important part of significant figures. So now that you know how to count the number of significant figures, you should now learn how to express your answers in the proper way of significant figures. So we will be dividing this into operations. First case is for addition and subtraction. So the rules for addition and subtraction are very simple. For addition and subtraction, the result should contain the least number of decimal places as given in the original numbers. So we are not even depending on the number of significant figures yet. We are just depending on the number of decimal places. So let's see if we have an example. Okay. So in this first example, you have 12.0372 plus 1.23. The first number has 4 decimal places. The second number has 2 decimal places. Therefore, in the final answer, you will only be retaining 2 decimal places. Okay, the least number of decimal places. So we can skip all of these other examples. For both addition and subtraction, you only follow the least number of decimal places. This gives you an idea that in exams, you cannot place as many decimal places as you want in your final answer. You have to depend on the given. Okay? It irritates me to see so many decimal places that are unwanted in the final answer. Our exams, just to remind you, are all online exams, and some of those you would be required to input a specific answer in a blank, and Blackboard will not recognize that if you exceed or if you exceed or if you lack the correct number of significant figures. So you need to pay attention to this. Now, for multiplication and division, the result should contain the least number of significant figures as given in the original numbers. So for addition and multiplication, we count decimal places. For multiplication and division, we count significant figures. Okay, let's have this example. 2 times 4.23. 2.000 times 4.23. Okay, so first and foremost, you already know the answer. The answer to this is 8.46. But the question is, how many significant figures should we retain? We can have the answer 8.460000, no? Because we have, sorry, 3 zeros, because we have 3 zeros in your given. Now, you simply count the number of significant figures. For the first one, you have 4 significant figures because all of these zeros are counted as significant because they are to the rights of the decimal place. Your second given has 3 significant figures because they are all non-zeros. Therefore, in your final answer, we should only have 3, sorry, in the final answer, we should only have 3 significant figures. That is the least of the two. Therefore, the final answer should only be 8.46. So that is how you apply the rules of significant figures uh, to multiplication. Of course, in this case, it's quite easy because our answer is just 3 significant figures anyway. But in some cases, let's say for example that the real answer is 8.4621893, etc., and so on and so forth. I do not want you to write this uh, entire number in your final answer in your exam. You need to apply the rules of significant figures, okay? Because all of these digits here are not significant, meaning they are not important. Okay, going back. So skipping these examples. For measurements, I would also be skipping this. This is irrelevant. Basically, you just need to rely on the number of significant figures of the given to determine how many significant figures do you have in your final answer. Okay. Now, we go to the important parts of this lecture, and that is the conversion of units. I know that some of you already know how to convert units. Some of you might be a little bit behind, so I would be making this as basic as possible for you to be able to follow. So this conversion of units is very important because oftentimes you would be given a problem with mixed units. Some quantities are in SI, some quantities are in English units. So you need to know how to convert from one unit to the other. We will be using, particularly in this course, we will be using the unit factor method, also known as dimensional analysis. We are using this particular style because we can also use it in stoichiometry. So, okay, so that you would already be familiarized now with this technique. I would just like to highlight some of the most common conversion factors. So you have 1 inch is 2.54 centimeters, 1 milliliter is equal to 1 cubic centimeter, 1 hectare is 10,000 square meters, 1 gallon is 231 cubic inches, 1 kilogram is 2.2 pounds, 1 minute is 60 seconds, 1 hour is 60 minutes. So these are not all of these are not all the available conversion factors. These are just some of the most commonly used that you need to be aware, or you need to know, no? As a future engineer, you need to know these conversion factors even at will, because you might be needed to perform on-the-spot computations or on-the-spot estimations, and these are very important. Okay, let's try this example. Convert 12.43 meters to inches. Okay. Using the dimensional analysis method, or the unit factor conversion method, you first start with a given 12.43 meters. And basically, we are using here ratios. So ratio, there is a number at the top, there's a number at the bottom, or there's a numerator and a denominator. What you want is, we want to arrive at the desired unit. We want to arrive at inches at the top. But then what the given unit or meters here should be the first unit at the bottom of the factor. So since we are starting with 12.43 meters, you write the units at the bottom, meters, and you write the desired unit at the top, inches. Basically, we are asking how many inches are there in 1 meter, or how many meters are there in 1 inch. If you know the direct conversion, you may use it. But if you do not know the direct conversion, we can use several steps. So let's first try the direct method. Okay. For the direct method, I know that for that 1 inch is equivalent to 0.0254 meters. So I know that conversion factor. That's why I was able to perform this calculation directly. So let's first calculate this. You can try calculating this using your calculator to follow along. This is 12.43 divided by 0.0254. We get the answer 489.37 inches. But we need to follow the rules of significant figures. So we have four significant figures on your given. So therefore, we can only retain four significant figures. You have 489.4 inches. This should be your final answer. That is how we convert. Okay, you convert. You take a look at the value and then think if you need to apply the rules of significant figures. So this is the direct method. Now, if you do not know the direct conversion of 1 inch is 0.0254 meters, then you can try the incremental method or the step-by-step method. Okay, it's longer, but it's simpler because you don't need to memorize a lot of conversion factors. Let's start again. 12.43 meters. We want to convert it to inches. So for the first conversion, you might want to go with meters to centimeters, because it's easier to remember that 1 meter is equal to 100 centimeters. So that's what we are going to do. For the first factor, we use 1 meter is equivalent to 100 centimeters. And to go from centimeters to inches, you know that 1 inch is 2.54 centimeters. So you can use that as the next factor. 1 inch at the top is equal to 2.54 centimeters at the bottom. So you can kind of see a pattern now. Whatever unit is at the top, we want to match that with the same unit at the bottom so that we can cancel it. So centimeters will cancel, as well as meters at the top, meters at the bottom would cancel, and the only remaining unit is inches. So if you perform this calculation, we should be able to arrive with the same answer. So that is 12.43 times 100 divided by 2.54. So that is also 489.4 inches, retaining the four significant figures on the final answer. That is how we convert using the dimensional analysis method or the unit factor method. Okay? Okay, so we have the same answer. That's 489. Sorry, we have the same answer, 489.4 inches. This is another example. Converts 10,523 cubic inches to liters. So let me first write that. So our given is 10,523 cubic inches. We want to convert that to liters. Okay, in this case, we don't have a direct conversion, or we don't know, let's assume we don't know of a factor that takes us directly from cubic inches to liters. We have to do this step by step. So you need to come up with a plan. So let's say, for example, my plan here is to convert inches to something that I already know. So I already know how to convert from inches to centimeter, right? Because 1 inch is 2.54 centimeters. So how do we go from centimeters to liters? The problem here is we are talking of cubic values. So cubic inches, I can convert that to cubic centimeters, and the cubic centimeters can be converted to milliliters. We know that 1 milliliter is equal to 1 cubic centimeter, and then the milliliter can be converted to liters. So this is a three-step process, and I will show you how the process works. We start with 10,523 cubic inches, which, by the way, contains 5 significant figures. So we expect to also have 5 significant figures in the final answer. First, unit conversion. Inches at the top. Therefore, I need to match that with inches at the bottom. And at the top is centimeter. But this is cubic inches. So we also have cubic inches at the bottom. Therefore, this entire factor should be raised to 3. So this is very important. Okay? So our conversion, 1 inch is equal to 2.54 centimeters. And if you cube that, that would be the equivalent of 1 cubic inch is equal to 2.54 cubic centimeters. So that is how we convert from a linear scale to a cubic scale. Okay, next factor. The cubic centimeter, I want to convert to milliliters. So we know that the conversion is 1:1. 1 milliliter is equal to 1 cubic centimeter. And then the last step, we need to convert from milliliters to liters. And we know, because this is just a prefix, that 1 liter is equivalent to 1,000 milliliters. If you take a look at the cancellation of units, cubic inches cancel. This would also be the denominator of this factor would also become cubic because we raised everything to 3. Cubic centimeter would cancel. Milliliters would cancel. The only unit that remains is liters. And you can input that to your calculator and retain 5 significant figures coming from our given. So that is 10, 5 to 3 times 2.54 cube. Do not forget the cube divided by 1,000. The answer in 5 significant figures, 172.44 liters. That is our final answer. Okay, so let's see if that agrees. Okay, we have here, sorry, in the lecture we have here the step-by-step procedure, and we have all of the factors, and we arrived at the same answer. So that is how you perform dimensional analysis. So again, I am teaching this to you because this would be useful in our stoichiometry later on in this term, no? But also in the conversion of units. More examples. I will be leaving these examples to you, no? So for you to be able to practice. Okay, for the last part of this lecture, this is a bit tricky, but this is very important. We will be talking about dimensional homogeneity. What is dimensional homogeneity? And why is it important in the study of chemical engineering calculations? For any equation to be true, because it's called an equation, the quantities on both sides of the equation should be equal. You already know this. The right-hand side of the equation should be the same or should be equal to the left-hand side of the equation. That's why it's called an equation, because the both sides are equal. Now this should also hold true for units, not just for the values. Okay? That's okay. The same is true for its dimensions. Okay, let's take a look at this case. Case number one. Can we divide 8 meters by 2 seconds? So to show you, can we divide 8 meters by 2 seconds? If there were no units, if I was just asking you, what is 8 divided by 2? And even if you're still in elementary, you know that the answer is 4. That's a very basic equation. No? 8 divided by 2 is 4. But when we are already including units, they should also appear at the other side of the equation to make it true. The answer to this is if we divide 8 meters by 2 seconds, the answer is 4, but we also need to include the units meters per second. This makes this equation correct because we balanced both the numerical values on the left-hand side and the right-hand side, and we also balanced the units. So if it's meters per second on the left and it's also meters per second on the right side. Okay, that's what we mean by dimensional homogeneity. Let's go back. Let's take a look at the other example. Can we subtract 2 meters from 8? Sorry, can we subtract 2 seconds from 8 meters? So how would that look like? We are subtracting 2 seconds from 8 meters. Is this possible? This equation is impossible because there is no way that you can subtract seconds from meters. You cannot subtract time from a unit of length. If we are able to remove the units, if we just retain the numbers 8 minus 2, that's a very easy answer. That's 6. But the same is not true for the one with units. So 8 meters minus 2 seconds is not equal to 6 meters because there's no way that you can subtract seconds from meters. That's where dimensional homogeneity becomes important. No? We want to avoid the latter scenario wherein we are forced to subtract or add non-matching units to obtain an answer because it's impossible. Okay, so let's go back to the lecture. Okay, this is an entry-level example for dimensional homogeneity. Consider the equation used to determine the gauge pressure. Let me acquaint you with this equation. It's pressure is equal to rho, the density, g, the acceleration constant due to gravity, and h, the height. The question is the equation dimensionally homogeneous? So let's go to our whiteboard. The equation is pressure is equal to rho g h. We are asked if this is dimensionally homogeneous. So let's examine. For this, you need to be determining what are the base SI units of the quantities. So let's dissect it. For pressure, the base SI unit is pascals. Pascals can further be decomposed into other base units. Pascals, if we decompose it, this becomes newtons per square meter. And the newtons can still be decomposed into its base units. 1 newton or a newton is simply kilogram meter per second squared. Okay, basic, right? We were able to determine what are the base units of pressure. Next, density. Back from our example later, you know that density is mass over volume. So in base SI units, that is kilograms per cubic meter, mass over volume. G, acceleration due to gravity. The value is 9.81. The unit is meters per second squared. Last, height. Height is just a quantity pertaining to length, so it's a base unit, it's meters. So let's see if this really is an equation. We will be able to say that this is a true equation if the units on the left side, the pressure, would be equivalent to the units on the right side, the rho GH side. Okay, so let's see. For the pressure side, we have pascals, and pascals is Newton per square meter, and Newton is kilogram meter per second squared per square meter. So that is the decomposed units for pascals. That should be equal. If we are talking of units, we don't use the equal sign alone. So we use the equal sign with brackets to designate that we are comparing units. Okay. The density or the rho, that's kilogram per cubic meter. G is meter per second squared. And then H is meters. We will mathematically manipulate the left-hand side of the equation to see if they are equal, or both the left and the right-hand side of the equation. So to simplify the left-hand side of the equation, the meter would cancel. One of the meters would cancel. So we will be left with kilogram per meter per second squared. Right? On the other side of the equation, what will cancel? In the denominator, there are 3 meters. In the numerator, there are 2 meters. So the 2 meters will cancel, leaving 1 meter on the denominator. Also, second squared is in the denominator. In the numerator, the only one remaining is kilograms. If you compare those, so those are similar. Therefore, the equation P is equal to rho GH is dimensionally homogeneous. And we can say that this equation is a true equation because the units on both sides are matching. That is how we decide if it is dimensionally homogeneous or not. Okay, if you are presented with a problem wherein the equation is not dimensionally homogeneous, then it's impossible to solve the problem correctly. There's a problem with the problem. Okay, so you always need to check if it's dimensionally homogeneous. Okay, how do we, sorry, how do we apply the concept of dimensional homogeneity to our problems? So take a look at this example. Suppose that the following reaction is dimensionally homogeneous. The composition, C, with units kilograms per liter, varies with time t with units of seconds according to the relation C is equal to 0.03 e raised to negative 2 t. So let me write that down. C is equal to 0.03 e raised to negative 2t. C has units kilograms per liter and t has units seconds. So the question is, what should be the units of the constants 0.03 and 2? You are presented with this problem. So obviously, in the equation presented, the units are not shown because we normally do not place units in these types of equations. We are tasked to find what are the units of those constants. Okay. Some basic concepts. First, for exponents or for exponential functions, normally we do not want any unit remaining in the exponent because that would pose some problems on how we can express those units if they are in the exponential form. That gives you a clue that the term e raised to, so e raised to negative 2t, that gives you a clue that this should be dimensionless. When we say dimensionless, what we really mean is that the quantity e raised to negative 2t should not return any unit. Okay? No unit at all. So how do we do that? So if you take a look at the exponents, negative 2t, wherein time is in seconds, and you are tasked to find the unit of 2. What would be, or what could be, the unit of 2 such that if you multiply 2 by t, the seconds would cancel out so that your result would be no units? Okay, I would repeat. What would be the possible unit of 2 such that if you multiply it by seconds, the resulting number has no unit? So it's actually quite simple. If we talk about the units, if I multiply seconds, or s, if I multiply that with 1 over s, the s would cancel. Therefore, the result is just 1, or there's no units. Therefore, if t has units of seconds, the constant 2 must have units of 1 over second, or per second, in order for them, when you multiply them, to be dimensionless. So therefore, 2 has a unit of per second, or 2 is second raised to negative 1. That is its unit. Because we know that the exponential function should be dimensionless. Okay, so that is one tip that I can give to you. So you look for the exponential functions. This also applies for logarithms, no, or sine, cosine, no, tangent, etc. We normally don't want any units remaining, so we want to cancel it out. Next, if you take a look at the entire equation, C is equal to 0.03 e raised to negative 2t. The concentration of C is kilograms per liter. On the other side, we also want it to become kilograms per liter. So let me just write a comparison of units. On the left-hand side, we want the unit to be kilograms per liter. On the right-hand side, we also want the units to be kilograms per liter. Now, on the equation, you have two factors. Let me divide that. The first factor is the 0.03 constant. The second factor is e raised to negative 2t. Now, from the previous calculation, we know that the entire e raised to negative 2t is dimensionless, meaning it has no units. So if you multiply something without units to something with a unit, the unit will not change. Therefore, by deduction, we can say that the unit of 0.03 is kilograms per liter. Now, if you want to check, we can check. So let me write 0.03 kilograms per liter. If you want to check, you need to write the entire equation including the units. So let's write it with units. Okay, the equation now stands that C with units of kilograms per liter is equal to 0.03 with units of kilograms per liter multiplied by e raised to negative 2 with units of per seconds times t with a unit of second. Take a look at the cancellation of units. Seconds will cancel, and the remaining units are, on the left-hand side, you have kilograms per liter. On the right-hand side, you also have kilograms per liter. So you know that that equation is dimensionally homogeneous, and our deductions led us to the conclusion that the constant 2 has a unit of per second, and the constant 0.03 has units of kilograms per liter. Okay, so that is how we use the concept of dimensional homogeneity to deduce what are the units of some constants. Okay, okay. Last, we have dimensionless quantities. Dimensionless quantities are scattered throughout chemical engineering. No? You will be encountering them in your major subjects. So dimensionless quantities are useful in simplifying complex equations in engineering. They are called dimensionless because they have no units, or if you simplify their units, it will just return 1. Okay, as an example, let's check if the following quantities are indeed dimensionless. One of the most famous dimensionless numbers in chemical engineering are the Reynolds number and the Prandtl number. You will be encountering this in your transport phenomena and fluid mechanics. So let me write the Reynolds number. Reynolds number is d or diameter, u or velocity, rho density divided by mu or viscosity. Okay. So let's check if it's dimensionless. If it's really dimensionless, it should return just a unit of no units, or the ratio of the units would just return 1, or everything would cancel. So let's see. The diameter is a unit of length. Its base unit in SI is meters. Now, next, velocity or U, base units meters per second. Next, density. Base units are kilograms per cubic meter over viscosity. Now, viscosity of liquids have base units of Pascal times seconds. We need to be able to reduce all of this to a dimensionless quantity, or every unit should cancel. Let's first decompose pascals, because Pascal is the only unit here that is not a fundamental unit. So let's decompose Pascal. If we simplify the numerator, we get kilogram square meter per second cubic meter. So that is our simplified version of the numerator. In the denominator, Pascal would be decomposed as kilogram meter per second squared per square meter times second. So with uh, so all of these units are now basic units, or they are now all fundamental units. So we just need to simplify to see if everything will cancel. So let's see. In the numerator, meters, square meters would cancel. That would leave meter in the denominator. So that's kilogram per second per meter divided by, in the denominator, what would cancel? Let's first simplify. So this becomes the meter squared would say in the denominator. So this become kilogram meter second per square meter per square second. See what will cancel. The meter would cancel, and then second would cancel. You will be left with, in the numerator, you have kilogram second per meter. In the denominator, it's also kilogram per second per meter. It's exactly the same, and it cancels itself. Therefore, the Reynolds number is truly a dimensionless quantity. Okay? It has no units. It's dimensionless. Later on in your major subjects, you will be encountering all of those. So if you want to practice, you can also try with the Prandtl number. So let me give you the uh, formula for Prandtl number. That's Cp mu over K. In the Prandtl number, Cp is heat capacity. The base units of heat capacity are joules per kilogram per Kelvin. You already know viscosity. Viscosity is Pascal seconds. And K is thermal conductivity. Thermal conductivity is watts per meter per Kelvin. So this is a little bit more of a challenge, because we are now introducing the units joules and watts. But uh, sorry, this is Prandtl number. But if you can solve this problem, then you will not have any problem with dimensionless quantities. Okay. Okay, so I will be leaving this example for you to practice as well. What should be the unit of H if the term H over CP needs to be dimensionless? So you are given here the units of G in English units, so you should also be practicing performing calculations on English units, and CP is BTU per pound mass per Fahrenheit. Okay, so you need to practice on this example, and I think that's the end of the lecture. Okay. That's the end of this lecture. If you have any question, please jot them down. This coming Sunday, I will be opening a Zoom room I'll be giving you the password and you can consult with me regarding something that I might have missed or something that might not be clear. So I will be available the entire day. Okay? Thank you for listening. Keep an eye for the next video lecture and as always, keep safe.